Welcome back, everyone. We're here in our natural language course, and we've talked so far a little bit about how machines can read text, but today we're going to really get into some nitty-gritty details. So if you look at raw text, it really is messy. There's lots of hashtags, symbols, misspellings, punctuation, things like that, and things that can potentially confuse a model. So what we're going to do today is look at how we can start to build a pipeline that cleans that up and turns that kind of chaotic text into something more structured that the models can understand. I've got a notebook here we're going to use to demonstrate some of these concepts. I'm going to run this first code cell. We're going to use the natural language toolkit to implement a lot of these capabilities. The first demo I want to look at is this messy text idea. So we can look at this and this sentence, and to us the meaning is clear. Whether loving is in all capital letters or lowercase, we understand that to be generally the same thing, maybe a little bit of different emphasis on the word, but the ASCII codes for a computer are different. There's the capital A, lowercase a is different. So in this first demo, we're going to use regular expressions to kind of remove the noise. We're going to compare the kind of the basic tokenization just by splitting, by removing the parentheses, like punctuation, and just having the words and comparing that to what tokenization does. And the tokenization is what the NLP algorithms are really going to see. So you can see here the raw tokens are just separated by spaces. The cleaned up tokens, there's more of them, and that's because we're separating out by apostrophes. You can also see we're standardizing to lowercase. And so we've also removed the punctuation. So hashtags, for example, in modern LLMs, we wouldn't do that because that's meaningful information. A hashtag signifies something important. But for right now, for our kind of more simpler exercises here, we're just going to go with the basic words. Now we have our tokens, but we've still got a problem. You see words like running, runs, ran, and those all refer to the same action. So we don't want our model to treat each of those as different, right? So what we do is there's a couple different techniques you can use. The first is a stemmer, and this is much faster. It's less computationally intensive, but it's pretty aggressive and not as intelligent. It kind of just chops off the ending of the words to try to get to a root. So let's go ahead and run this, and you're going to see that it doesn't always even give us real words. As you can see for university, it's just kind of universe without the E. Whereas if you look at the lematizer, so this is a much smarter, it's more like a surgeon would do. It's like specifically going in and finding the root of the word. It is a little bit slower by comparison, but is much more accurate. And this is generally what you would use. So previously when computers weren't as fast, we might have looked to use a stemmer. It still has some use cases, but generally you want to use a lematizer, and you can see the value. It can kind of standardize a lot of these things. Now we're going to notice one very interesting bit. This first one, running, the stemmer actually does a better job. It goes to run. The lematizer is running, and that's because as it is right now, the algorithm doesn't know whether it's using running as a noun, a verb, what the context is. So here's the problem. The lematizer by default doesn't know. If it doesn't know any better, it's going to assume that each word is a noun. And so running, it thinks that's what it is, and it just stays that way. So what we want to look at now is part of speech tags, or POS, that looks at the sentence and figures out, based on whether it's in a noun phrase, a verb phrase, and the context of the sentence, what role that word actually plays. So here, if we look at our table now, if you look at the very bottom, you can see that running, it's in VBG, which is a tag for the verb group. And so by default, we saw earlier, it lemmatized that to running, it didn't change it. But with the context, knowing the part of speech tag is a verb, it was able to get the root run action. And so that's what we want to see. So thus far, we've primarily been focused on individual words, but by themselves, it doesn't mean anything. They only have meaning in the context of the sentence that they live in, those sequence of words. Of course, that's what transformer models are all about, sequence to sequence translators. So we want to look at the relationships, and you can break down this part of speech tags. Really, they live within a hierarchy. So you can visualize this. Here I'm just defining a very simple grammar, and these token names here are noun phrase, DT is determiner, and JJ is adjective. So all of those are used to just build up a grammar that we can easily use with this regex parser class. And so now I can get this kind of nice, pretty looking hierarchical view of what the sentence is with a breakdown with the tag. So the computer was already starting to do this. This is an easy way for us to confirm we're getting what we expect. We've kind of danced around this concept of a grammar, so let's actually formalize that a bit. Here, this CNF grammar in the code, you can see gives you the structure of how the system figured out what those part of speech tags were. So at the highest level, you have S, a sentence, which in this simple grammar is made up of a noun phrase and a verb phrase. Of course, English language can be different. Commands often just start with a verb, but this is our simple grammar. We would only be able to understand if it came in this order. So then you would keep recursively going down. What is a verb phrase and a noun phrase made up of? You can see here how that breaks down until you eventually get to the hierarchical structure we just saw a moment ago. Now, there is a problem with this. If you look, noun phrase can be, it can be a determiner and a noun, like the apple, or it can also contain another noun phrase. And so a simple algorithm would have really get in an infinite loop when that happens. So the CKY algorithm is a dynamic programming algorithm that helps handle this. Let's go ahead and run this code. And what it does is it actually builds dynamically this table. And so you can see in our sentences, we're referring to each of the tokens by number. And here you can see noun, verb, determiner. And so it's able to manage, we only need to look at the upper right portion of this matrix. And that is how it can figure out, how it can handle a grammar that looks like this. So this has been a really quick tour on some of the basic parsing algorithms. Formal grammars are a fundamental concept of, they've been around for so long. Any programming language follows a formal grammar like this. That is why there's specific syntax that you need to follow, and it makes it easy to understand. And that's, of course, one of the main challenges of NLP is that normal English text has wildly different patterns. It uses slang. There's exceptions all over the place, and so you need to have a more intelligent system. But these are the foundations they're based on. So hope that was helpful, and I'll see you in the next video. Thanks.